This presentation will deal with buffer capacity and what makes a good buffer. So our objectives will define buffer capacity and use the concepts to determine which buffers will work best. And then we'll create and use a criteria for what makes a good buffer. So what is buffer capacity? Buffer capacity is the amount of acid or base that can be added to a given volume of buffer solution before the pH changes significantly. What does it mean by significantly? Usually more than 1 unit, which is a factor of 10 for the H+ concentration because pH is a log scale. So if you have a higher concentration of buffer, it will have a better buffer capacity. Why is that? You will have more ions available to react, so it takes longer to use them up. The pH of the buffer is the same in many cases, but the buffer capacity will differ. So if we have the same ratio of HA to A-, you will have the exact same pH, but if your molarities are different, you will have a different buffer capacity. So for example, a 1 molar solution, like 1 molar and 1 molar for acid and base, will have a lower capacity than a 2 molar, just because there's more stuff. Okay, if you have equal amounts of acid and salt, or base and salt, it'll have a better buffer capacity. Why is that? So a buffer may be made with an unequal number of moles of acid / base and salt, but that makes a limiting reactant, like it's built in. Whereas if you have them equal, that is less the case. Okay. So what makes a good buffer? It's a good buffer when it has an equal concentration of both components, because we just got from the previous slide that if we have an equal concentration of both components, it's going to last longer than if we have an unequal concentration, in which case we've created a limiting reactant sort of situation. 2. It should be composed of an acid-base conjugate pair with a pKa, and pKa is negative log of Ka, because anytime you put P in front of something, it's the negative log of the thing. Anyway, it should have a pKa near the pH of the target. So, by extension, weak acids are better buffers for a pH less than 7, weak bases are better buffers for a pH greater than 7, and generally buffers are not going to be useful when one component is only 10% of the other, as far as the amount. So anything where your pH and your pKa are not that close is going to not work that well. All right, let's use that information. Which of the following would make the best buffer for a pH 6.0? So we take a look, and we can automatically get rid of C and D because they are both bases. They have basic pKhs. We're talking about weak bases. Goodbye. All right, so now we have to choose between A and B. And we have 2 different pKa's, 3.750 and 4.74. We're aiming for 6.0, so we would get closest to that if we're at a pKa near that, which leaves us with B as our answer. That'll be the closest. Buffer capacity is greatest if there is a high concentration and the amount of conjugate acid equals the amount of conjugate base. A good buffer has a pKa close to the target pH, and it uses an equal amount of conjugate acid base and has a higher molarity.